Woo, we are live. This is Math 60 1.2 Part 2, and we are still talking about sets of numbers. Now, these are the sets of numbers we're going to be using in this class. It doesn't include all the sets of numbers, but it'll include all the way up to the real numbers, which are, again, the set of numbers we're going to be working with for 99% of the time in here. And then a brief flirtation with another set, and then back to this. So, when we had last left our heroes, we had talked about the natural numbers, the whole numbers, integers, and rational numbers. And now we're going to be talking about the set of irrational numbers. And we're going to start right off the bat with a big controversy, and that is that this book calls the irrational numbers H, which you could write again with the secret math language using that H with an extra line. That's just how people write it on boards and such. And this is the set of all non-terminating, non-repeating decimals. Now, that's not controversial. The controversial part is what you call it. And different books call this set different things because, well, when I went through math, I was taught it didn't have a name. It didn't have a letter that represented it, who knows? But I've seen different books use different letters. So we're going to go with H because that's in this book. And but the fact that it's the set of irrational numbers, not controversial at all. Absolutely. These are irrational from the word rational. They're not rational. So these cannot be written as fractions. Woohoo. So these are going to be really interesting numbers. Now, it turns out there are a whack ton of these numbers, way more than the set of rational numbers. This set is so much bigger. It's a bigger infinity. It's pretty amazing. However, because they are difficult to work with, we are not going to work with a lot of them. The fact that they are non-terminating and non-repeating means that if you want to write them out, you're going to spend the rest of eternity just writing one down as a decimal because it just keeps going and going and going. Examples of this are pi. Pi is a really well-known one. By the way, generally accepted spelling pi for that, or the Greek letter pi. And this is a number that's close to 3. And I'm just going to write it as 3.14 ... And these digits will keep going, and sometimes they get into an interesting pattern, but then they break themselves out of it. And the idea is irrational numbers, basically the list of numbers just keeps the decimal expression just keeps changing, doesn't repeat, doesn't stop, just keeps going. And a fun fact about pi is for a long time, and I don't know if this is still the case, but it may be, for a long time when I was younger, pi was used as a way to show off. It was used as a way to show off how great your computer system was, because there would be competitions to see who could find the next digit of pi. Pi is now known to many, 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 many digits, way more than I know off the top of my head, many more than your calculator will tell you. But basically the idea is you can just keep looking for digits of pi's for the rest of your life, your kid's life, their kid's life, etc., etc. So that is a famous irrational number. Another one that we're going to deal with in this class, but you probably haven't seen before, is the letter E, which represents a number that is 2.7 and then some stuff. And you'll notice that I'm using straight equal signs, not approximations. I am not rounding them. I'm telling you, yep, there's more. So when you use the ellipses, it's a straight equal to. If I wanted to say pi rounded would be approximately 3.14, if you want to do that, you would do the wiggly equals, and that's an approximate equals. We use that a lot. Sorry, I have to stop speaking when I'm trying to spell approximately. That means approximately. So if you're going to approximate it, you stop it. You end it wherever you're going to stop the approximation, and you put in the wiggly equal signs. But I'm putting in straight equals because I'm saying, yeah, there are more digits. I'm just not writing them down. Now, these two are really cool. They're called transcendental. It's a really special category. They are the super irrational numbers, not just, run of the mill irrational numbers like your neighbor, the irrational number. These are the superheroes of the irrational world because they're extra irrational. They are not the algebraic solution to an equation, or they are not the solution to an algebraic equation unless you put them in the equation. So that's pretty cool. And if what I just said was like blah, 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 that's okay. That's really okay. I'm just going to geek out. You guys hang tight. I'll be back in a second. Okay, some other more common irrational numbers. A number like that. Now, a lot of people call this the square root of 2. It's also known as radical 2. And basically, if you've got a number inside of a radical or a root and it doesn't turn out nicely, it's not something you can simplify, then it is irrational. And let's look at the calculator here. My handy dandy calculator. Ooh, look, I've been doing math. Okay, let me get this out of the ring light. There we go. And I'm going to show you that on a lot of Texas Instruments and many others, you've got a couple options for radicals. There is actually a square root key, and I know this may be very hard to see on this calculator, but it's up above. So in order for me to expand this as a number, I'm going to have to not just type in the key that has the square root, but I'm going to type in second. That tells me, or that tells the calculator to go, I type in the second key and then the square root. So it goes to the meaning up above rather than the meaning of the key. So I do second, and then in my calculator, there's an x squared with a radical up on top. That's what I'm looking for. And then 2, and then equals. So second, 2 equals. And you will see, let me get it out of the ring light. There we go. You'll see that you can kind of guess this is going to be irrational because the digits keep going. It doesn't just stop. It keeps going and it fills the entire screen. Now, a couple things about this. Your calculator knows more than it's telling you. So you never want to copy this down and use that number. Use your memory, retype it in with the calculator, keep it in the calculator when you're doing calculations. And as we get further along, I'll show you how the heck you're going to do that. So I see that this says 1.414. Notice it starts to look like it's going to start repeating, right? It looks like 1414, but then it breaks itself out of it. And then it's 1.41421, etc. So radical 2 is approximately 1.5, 1.41421, and then I'll do some ellipses. Same thing with radical 3, also an irrational number. That one I happen to know is close to 1.7. Now, I wrote down here, there's a little box. Note that some square roots are not irrational. For example, these square roots are rational. For example, if I take radical 4, that's actually equal to positive 2. So just because you put something inside a square root or a radical sign does not mean you get an irrational number. 2, well, heck, that's a natural number. It's also rational. So it's natural, it's whole, it's an integer, and it's also rational. Another example, radical 81, which equals, you're right, 9, yay. Also natural, whole, integer, and rational. So irrational numbers are numbers basically that just keep going. They don't repeat, they don't stop, they keep going forever. And so you're going to either have to use a calculator So again, I'll show you 3. Here's radical 3, 1.732. So this is 1.732, which is approximately 1.7. So that's how you would write it. I usually write the equals first and then you approximate it. This one I could, again, approximate about 1.4. It depends on, you'll have to pay attention to the problem. Some problems are going to ask you for more digits. I just did a single digit to the right of the decimal point there, but you could do a lot of digits. It depends on what you need. So these are the irrational numbers. They're going to be, for the most part, possibly the most squishy feeling numbers for you, because we don't work with them a lot because, let's be honest, they're pretty hard to work with. So a lot of the time we're going to be working with numbers that turn out pretty nicely for us for the things we're going to be doing. Now, don't worry if you happen to love these. These do come roaring back in all applications because, again, if you just pick a number at random, there's a good chance it's going to be irrational, not rational. Okay, so woohoo! The big set. Dum dum dum. Very, very much excitement. We've got a party going on here. Yay! Because we've gotten to the set of real numbers. Capital R. Now, capital R stands for the reals. That's why rational was a Q for quotient. Reals is R, and again, there is, of course, a fancy way to write it with the extra line. And this is all the numbers we've talked about so far. So we've got the natural numbers, the whole numbers, the integers, the rational numbers, the irrational numbers, and the set of reals. Okay, so N is the naturals. W is going to stand for the whole numbers. Z is the integers. It's interesting to me how the derivation of language, we've got natural numbers, whole numbers. You generally don't hear integer numbers. We just call them the integers. Q. Rational numbers or rationals. I've heard that. H. Irrational. So these guys are kind of like twins. There's no overlap. For the rest of these, there's a lot of overlap. Here, they're dividing up. It's like they've got a bedroom and one's going to sleep on one side, one's going to sleep on the other side. There's a line down the middle. They don't cross. And the whole set, the whole thing is the set of reals. So in this Venn diagram, much like the chinchillas and lizards and roses we were dealing with in the previous video, we want to set up the set of numbers. And let me remind you again, and you should be thinking through this too, because these are good to have memorized. The natural numbers, again, these are the numbers that are the counting numbers. 1, 2, 3, 4, 5, 6, 7, 8. Whole numbers starts with 0. How are you going to remember that? Well, notice that whole sounds like hole, like a hole in the ground. A hole looks like a 0. So that's how it's the set with the 0 attached. The integers, remember, these are the ones that look just like the whole numbers, except you're allowed to have negative ones. So plus or minus 1, plus or minus 2, plus or minus 3. So the negative ones are here. The rational numbers, remember, this is when we went to a set and we're like, putting them in order is really tricksy. These are all the fractions. There are a lot of fractions out there. All the little fractions that you would never think about, like when the denominator is like 14,587,632. So there are a lot of fractions. So instead of listing them like we did with these, we're going to use something called set builder notation and write A over B such that A and B are elements of the set of integers, and B better not be 0. And hopefully you watched my squirrels and pizzas video so you understand why B can't be 0. And you cannot put 0 in the denominator or else the sharks will eat you. Where are my sharks? Here we go. Here's the shark. Do 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 do. Okay. Irrational numbers. We're not going to write set builder or anything because these are iconoclasts. They're so different. There are so many of them. There's just no way to write them down or come up with a rule for them. So we're just going to say there, it's just the set of irrational numbers. And we're not going to try to represent that with anything. So notice the overlap. The natural numbers, 1, 2, 3, here we go, 1, 2, 3, 4, 5, 6, 7, 8, 9, etc. is right there. So the whole numbers are just the natural numbers plus a 0. And then the integers are just the whole numbers plus the minus, the negative ones. And then the rational numbers are just the integers, because each of these can be written as a fraction, plus all the other fractions. So the way we write the Venn diagram, the natural numbers come in the middle, in the smallest set is the natural numbers. And then this is the set of whole numbers. And I can specify that in the set of whole numbers, that it's just 0. That's the only thing outside the natural numbers, because that's the only thing that's different. And then the integers come here. And that would, in this yellow band, we've got the whole numbers all nestled inside. But then we also have like -1 and -17 and -483, etc. So all the negatives live in this yellow band. The rational numbers live here, this green band, and everything inside of it also rational. And then, so the question here is, where are the reals? And I claim that this set is the reals, at which point you're like, whoa, wait a minute, where are the irrationals? And I'll say it's going to be this blob over here. Something like that is the irrationals. The irrationals live outside the rationals. They are not part of the set of rational numbers. What do you guys think? Kinda, sorta? Kinda woohoo? See, I'm going to take a look. I think, given that we're at almost 18 minutes now, I'm going to end this video and then I'll start another one. So this was all about the sets of numbers. Next up, we're going to talk about prime numbers and divisibility with the integers and the whole numbers. Woohoo! I know, it sounds exciting. Okay, congratulations. You guys made it through another 18 minutes of class. Woohoo! Math on, guys.